Welcome to ECA Limu Learning Simplified, and welcome to this lesson. In the previous lessons, we have been discussing pressure in the two main states of matter, that is solids and liquids, where we said in solids pressure is equals to force or over area, and then in liquids we said pressure is equals to H rho G. However, we said H rho G can be used to calculate pressure in fluids, where we said fluids, these are substances that can flow, so it means liquids which can flow, and then gases are under fluids. Now, since we have been looking at the three or at the states of matter, then it means we have remained with the third state of matter, that is gases. So in this lesson, we are going to discuss pressure in gases. And here we are going to measure our discussion on atmospheric pressure which is caused by the air column around the Earth's atmosphere. And here we are going to see how atmospheric pressure is very useful, especially in helping us to suck liquids using a drinking straw and also maintain our blood in our bodies. Remember, if blood pressure in your body is higher than the atmospheric pressure, then you are likely to nose bleed. But now, why don't we nose bleed? Because the atmospheric pressure outside is higher than the blood pressure in our bodies. My name is Albert. I hope you will enjoy the lesson. By the end of this lesson, I expect you to be able to define atmospheric pressure and then perform a very simple experiment where you are going to prove that there is atmospheric pressure in the atmosphere. And then we are going to see the applications of atmospheric pressure, especially in the drinking straw. And then finally, we will look at examples of questions involving atmospheric pressure. So what is atmospheric pressure? Atmospheric pressure is the pressure exerted on the Earth's surface by the column of air around it. Around the Earth's surface, remember you were told in geography that we have an atmosphere, and in the atmosphere we have air. And in chemistry you were told air is a mixture of gases, and now gases are examples of a state of matter. So since matter has mass, it will also exert pressure or due to the air column. So in this case, in the atmosphere, as you can see on the screen, there is air, and this air increases or decreases as you move outside the Earth's surface. So when you are on the Earth's surface, what you have, the density of air or the amount of air that is there is very great. But as you move out, the amount of air decreases as you move out. And if the amount of air decreases as you move out, it means the mass of the gas will be decreasing as you move out. And if mass decreases, remember now, weight of the gas will also decrease. And since pressure is force per unit area, and that force we are going to use weight of the air, then it means the pressure will be very low. When force is low, pressure is low. So as you move out, pressure of the atmosphere decreases, or atmospheric pressure decreases. And you can see on the screen, close to the Earth's surface is very dense. It means the atmospheric pressure is very high. As you move out, it fades away until where you will not get atmospheric pressure anymore. Now, we are going to realize here, it is the reason why people on high altitude nosebleed, especially when their body is not in good condition. Now, if someone is up here, it means now the atmospheric pressure is low. If the blood pressure is high, this person is likely to nosebleed. And the reason is the person is at high altitude, the atmospheric pressure is low, the pressure in the body or the blood pressure is high, then now fluids, that is blood, will move from where there is high pressure to where there is low pressure. Another important to note is that the SI unit of atmospheric pressure is atmosphere, and it's denoted by ATM, small letters. And the relationship between an atmosphere to newtons per square meter is that 1 atmosphere is equals to 103,600 Newton per square centimeter, which is the same as 1 atmosphere is equals to 760 millimeters of mercury. We are going to say that. Now, since we defined science as a systematic method of acquiring new knowledge and even testing existing knowledge, now we have an existing knowledge of atmospheric pressure. Since we don't have to wait just reading the books and know that there's atmospheric pressure, then we can perform an experiment where we are going to test the knowledge of atmospheric pressure, and it's called a crashing can experiment. In a crashing can experiment, what you need a can, and then you need some water and a source of heat. So you put the water inside this can, some water, not too much, some water. Let me just indicate using blue. You need some water up to that level, and then you heat. As you heat, remember, we have said outside here, and we are going to see there is what we call atmospheric pressure. Atmospheric pressure is a pressure which is caused by air around this container. So as you heat, there is atmospheric pressure around here. Then inside here now, there was air. Before heating, there was air. This air will be expelled by the steam which will be generated. The air will be expelled out. Air will be expelled out. This is air which will move out. And then inside here now we will remain with the steam. Steam, remember, it was water which was at this level down here. Now the container will remain in that state because the steam also exerts pressure outwards. The steam inside here exerts pressure outward, so it means the can will remain in that shape. Now the can will remain in that shape although air has been expelled, because steam will exert pressure outside, and then atmospheric pressure will be exerting pressure inside. Now, after some time, after the water has boiled for some time, you stop heating, you close the hole up here using a cork or a stopper, and then immediately you pour some cold water. You pour some cold water on the outer part of the bottle. Now, what will happen? What will be observed is that immediately you pour some cold water, the bottle will crash inside. That is the observation that you will make. After heating, you have expelled air, and then now you put a stopper and you pour some cold water, the bottle will crash inside. Now, what happens? Let's go back when we were heating. When we were heating, we generated steam. We generated steam, and the steam occupied this space and even expelled the air. Also, let's say this was steam which occupied this space, the one which was pushing the boat outside, balancing with the atmospheric pressure. The air which was there was expelled, so it means this space remained with the steam. Now, when you cool, remember, steam is water but in gaseous state. When you cool, the steam, which is water in gaseous state, will change its state from gaseous to liquid and come back down here to become water. So in that case, this steam, after cooling, the steam disappeared. The steam cooled to become water. And this space now, since there is no air and you have put a stopper there, then it means that space will remain almost empty. Almost empty spaces in physics, we call them partial vacuum. Partial vacuum. So this space will remain a partial vacuum. Now, when it remains a partial vacuum, it means it's almost empty. Now, an empty space cannot exert pressure, because we said you can only exert pressure when there is mass. The mass which was here of gas was expelled. So it means now the atmospheric pressure, which is now high, because outside we have atmospheric pressure, we have not heated anything there. The atmospheric pressure, which is high from outside, will push the bottle to the inside, which is empty. So this bottle will crash due to pressure difference. The pressure difference between the outside we have high pressure, we have high pressure, and then inside we have low pressure. Low pressure because we have cooled, the steam has gone back to liquid. So the difference in pressure between outside pressure, which is very high, and inside pressure, which is very low, is the one which makes the outside pressure to win and crush the bottle inside. So the essence or the purpose of heating this bottle and water was to expel the air. Then we leave a partial vacuum, and then we will see, will this bottle still balance? We are going to find that it does not balance. The pressure outside will outweigh the pressure inside, and then it will crush the bottle inside. Now, one of the applications of atmospheric pressure is a drinking straw. And a drinking straw, we use it almost in our everyday life in drinking juice and soda and even milk. Now, when you put a drinking straw inside that liquid, the level of water inside the liquid and inside the straw is almost the same, except some few adhesive force which makes it rise slightly inside the straw. Now, what happens, what makes them to be almost at the same level is because of balanced pressure both inside and outside the straw. The pressure outside the straw is balanced by atmospheric pressure, and when the straw is opened from the top, it also experiences atmospheric pressure inside because there will be a gas inside. Now, when you want the liquid to rise into your mouth, what do? You suck. When you are sucking the air which is inside the straw. So the straw will remain almost empty. When the straw remains almost empty, it means atmospheric pressure inside the straw will be low. So here we will have low atmospheric pressure. When you have low atmospheric pressure and outside we have high atmospheric pressure because we have not sucked the air there, then in this case, it will force the liquid now to go down and go inside the straw to occupy the space which has been left by the air which has been sucked. Now, in the process of occupying that space, it will find the old straw is empty, and then the liquid will rise into your mouth. And when you stop sucking and you remove your mouth, the level again will balance outside and inside. And then when you suck again, the liquid will rise or will come, you will create pressure. In short, you are going to create pressure difference between inside the straw and outside the straw in such a way that inside the straw, we have low pressure when sucking, and then outside the straw, we have high atmospheric pressure. Now, this pressure difference is the one which makes the liquid to rise because fluids will flow from where we have high pressure to where we have low pressure. So, from what we have just seen, we can conclude that if we have any substance on the Earth's surface, this is the Earth's surface, and you have a boy here, this boy is experiencing atmospheric pressure. If you have a stone or a ball, the boy is playing the ball is also experiencing atmospheric pressure. But now the question comes, what if you have a beaker containing water? A beaker containing water up to that level, and this beaker, this water, it has some height h. At the opening up there, it is experiencing atmospheric pressure. That's what you have seen, atmospheric pressure. But now, what about a particle or a stone which is inside this water? Because we said before you have even atmospheric pressure, if a particle is down there, it will experience pressure due to this height h. And if you know the density of the liquid. But now here we are saying above the liquid, there is atmospheric pressure. So it means This particle here, let's call it Q. The particle Q will experience a total pressure of 1, it will experience atmospheric pressure, the one which is there automatically due to air column, and then 2, it will experience H rho g, pressure due to the height of the liquid. Therefore, a particle which is inside a liquid will experience 2 types of pressures. So the total pressure experienced by particles inside a fluid on Earth's surface will be total, or pressure total, is equals to pressure due to the atmosphere or atmospheric pressure plus pressure due to the height of the liquid column, which is H rho g. This is very important to note. So long as you have anything inside on the Earth's surface and it's a liquid, it has to experience 2 pressures. One is due to the atmosphere, and then the other one is due to the height of the liquid. Now let's do an example involving the ideas that we have discussed. The question is, a sea diver is 12 meters below the surface of the sea water. If the density of the sea water is 1.03 grams per cubic centimeter and the gravity is, or gravitational field strength is 10 newtons per kg, determine the total pressure on him. Take atmospheric pressure to be 103,000 newtons per square meter. So here we have a diver. A diver is here. This is the diver. And then this is the water on top of him. And this diver is 12 meters below. 12 meters below. And then this is the surface of water. This is the surface of water. Remember what we have said, anything which is on the Earth's surface will experience atmospheric pressure. So here we have atmospheric pressure. And then this diver now is again inside water. He will experience pressure due to H rho g. So he will experience 2 types of pressures. Now they want us to get the total pressure. Now in this case we have said total pressure is equals to pressure due to the atmosphere plus H rho g. Now pressure due to the atmosphere, we are given 103,000 newtons per square meter, then plus H rho g, H is 12, then density we have in grams per cubic centimeter. If we convert it to kgs per cubic meter, it will be 1030 kg per cubic meter. Remember, you multiply by 1000, then times 10 newtons per kilogram. This one will give us H rho g. So this one is H rho g on this side. Then now to solve this one, total pressure will be equals to 103,000 newtons per square meter plus 123,600 newtons per square meter, which is going to give us a total of 226,600 newtons per square meter. So it will give us 226,600 square meter. So total pressure, you add the pressure of the liquid, that is H rho g, plus atmospheric pressure, which is automatically there. So that is the end of our lesson today. For more questions like this one and others, kindly visit ECLIMU. There's a website link down there. You will find more questions and solutions on the same. And if you have any difficulties, just make a comment below this video and we will solve it as soon as possible.